I'm Will, and this is the second of 4 videos I've made summarizing the projects I've worked on here at Princeton. This video focuses on the thruster that I use for my research, as well as the thrust measurement system. I work on a type of high thrust density device known as an applied field magnetoplasma dynamic thruster, or AF-MPDT, sometimes also referred to as an applied field Lorentz force accelerator. But basically, it's a plasma cannon with a force field nozzle. We'll start by taking a look at how this thruster works, and then I'll tell you about some of the research that I've done to determine how to make it work better. Our thruster resides in a steel tank, and this material was chosen over fiberglass because we wanted to be able to handle as much as 100 kilowatts of power, and a lot of that power is going to heating the walls, which would melt fiberglass. You can see that the cooling lines are welded to the interior to keep it from getting too hot. I work with both lithium and argon propellants, but each requires its own thruster. This is the lithium Lorentz force accelerator, or LILFA for short. This is an electric rocket. The physical nozzle serves as the anode in the electrical circuit. The object in the center is the cathode. This particular cathode is known as a multi-channel hollow cathode. Inside the cathode is a graphite heater, which causes the cathode to glow white hot before ignition. There is also a tube through which the lithium flows and where evaporation takes place before venting through the many channels. Both the anode and cathode are made of tungsten, since it has a higher melting temperature than any other metal. Using lithium as a propellant is problematic for a researcher, since it is extremely hazardous, it takes a long time to clean up, and because it coats everything in an electrically conducting layer. But it offers an equal number of advantages for thrusters. In addition to having a low ionization energy, which means that more energy can go to thrust generation, it lowers the work function of the cathode. This feature is essential because without it, our tungsten cathode would melt. How does the LILFA generate thrust? There are 3 different thrust generating mechanisms. First, just like in a chemical rocket, there is a hot gas expanding through a physical nozzle, generating the gas dynamic thrust component. When we strike an arc through the plasma and increase the current generates an azimuthal magnetic field. In this case, the Lorentz force, or cross product of the radial current and azimuthal magnetic field, is primarily along the thrust axis. This component of thrust is known as the self-field thrust, since it results from the self-induced magnetic field. You may have noticed the large cylinder surrounding the thruster. This is a solenoid. It contains a copper pipe that has been twisted a number of times around the thruster. This pipe carries cooling water as well as large electric currents. These currents result in an axial diverging magnetic field. This is the force field I referred to earlier. It confines the plasma in what is known as a magnetic nozzle. You can actually see the boundary of this magnetic nozzle when operating at high magnetic field strengths. In addition to extending the physical nozzle, the applied field results in a Lorentz force that acts to swirl the plasma. As the swirling plasma expands through the magnetic field, the rate of rotation slows in order to conserve angular momentum. In order to also conserve energy, that means the plasma must accelerate in another direction. In this case, that is along the thrust axis, which results in the generation of thrust when the plasma detaches from the magnetic field. This thrust, along with any force resulting from Hall currents, is the applied field thrust component. This last thrust component is the dominant one under typical operating conditions, and the one that has proven most difficult to model over the last 60 years of applied field MPDT operation. We want a formula with which we can predict the thrust for a given power level, magnetic field, geometry, mass flow rate, and propellant species. And we want this because such a model can be used to optimize the thruster for a given mission's requirements. Many models have been put forward to date, and experiments suggest that thrust scales proportionately with the current, magnetic field strength, and anode radius under most conditions. However, prior to my studies here, all measurements in the literature were of the total thrust, which is the sum of all thrust components. Without perfect gas dynamic and self-field thrust models, it is therefore difficult to validate a model for the applied field thrust component from a measurement of the total thrust. I constructed a new thrust stand for the LILFA in order to make direct measurements of the applied field thrust component. This thrust stand operates on the principle of an inverted pendulum. When the thruster applies a force, the pendulum moves. I measure this motion and calibrate it against a known force to determine the thrust. In order to measure a single thrust component, I first fixed the thruster to the lab frame. Then I separated the solenoid from the thruster. Because the solenoid generates the applied field, the force resulting from that field must generate an equal and opposite force on the solenoid. The solenoid is then suspended from a structure supported by 2 copper pipes. These pipes carry all current and cooling and act as springs for the inverted pendulum. Now, if I turn on the thruster with the applied field turned off, nothing happens. But if I increase the magnetic field strength, the applied field thrust component will cause the solenoid to deflect. I measure that deflection using both an LVDT and a proximeter, each of which is contactless. In order to determine how that deflection corresponds to a force, we can apply a known force along the thrust axis. In this case, we have a thin wire traveling over a low friction pulley and down to a scale. That scale can be triggered by a remotely controlled actuator. The force applied to this scale is known as a function of the position of a mass, which is also remotely controlled, and which can be used to match the deflection found while firing. That's an applied field thrust measurement in a nutshell. It's a little more complicated when you account for thermal drift and electromagnetic tear forces, but now you understand the basic principles. Using this thrust stand, I have shown the applied field thrust component to be dependent on mass flow rate, which had not previously been shown. My theoretical work related to the applied field thrust is less suited to a video format, so if you are interested in that, you can visit our lab website at alphane.princeton.edu, where all of our papers are posted. That concludes the second video. The next video will focus on measurements of plume divergence using a new type of condensation measurement device known as the dynamic resistance probe.